What is film capacitor and how does it function? Its application. Film capacitors are electrical capacitors that use a thin plastic film as the dielectric material. The film is usually metallized and layered with electrodes, allowing for an efficient storage of electrical energy. Film capacitors are widely used in electronics due to their reliability, stability, and high insulation resistance. Construction of a film capacitor. Film capacitors are constructed using a layered design with a dielectric material made of a plastic film and electrodes. The construction can vary slightly depending on the type of film capacitor, but the general components and structure are as follows. 1. Dielectric material. The dielectric is a thin plastic film made of materials like polypropylene, PP, polyester, PET, polystyrene, or polycarbonate. The choice of dielectric material affects the capacitor's characteristics, such as its capacitance stability, temperature resistance, and voltage rating. 2. Electrodes. Electrodes can either be metal foils, aluminum, or metallized films. In metallized film capacitors, a thin layer of metal, aluminum, or zinc is vacuum deposited directly onto the plastic film, which reduces the overall size of the capacitor. Foil capacitors use separate metal foil layers along with the dielectric, which provides better performance under high currents but makes the capacitor bulkier. 3. Winding of the film. The plastic film and electrodes are wound into a cylindrical roll or sometimes a flat pack, also called stacked. The windings are tight to ensure compactness. This winding process creates the layered structure where alternating layers of the dielectric and electrodes are arranged. 4. Connection to terminals. The ends of the windings are sprayed or connected with metal, usually zinc or aluminum, to form contact points with the electrodes. Wires or terminals are attached to these contact points for electrical connection to a circuit. 5. Encapsulation or enclosure. The wound element is enclosed in a plastic or metal case for protection against environmental factors like moisture, dust, and mechanical stress. Some film capacitors are filled with resin or epoxy to enhance durability and increase insulation. 6. Additional features. Safety features. In certain applications, the capacitors include internal fuses or special self-healing properties. In self-healing capacitors, usually metallized film types, small dielectric breakdowns caused by high voltage automatically heal. The metal layer evaporates around the point of breakdown, restoring the insulating properties without significant loss of performance. Axial or radial leads. Film capacitors may have leads or pins for mounting on circuit boards. Radial leads come out from one side, while axial leads extend from both ends of the capacitor. Common types of film capacitors based on construction. Metalized film capacitors. Use metallized film electrodes. More compact. Feature self-healing properties. Film/foil capacitors. Use separate metal foil electrodes. Capable of handling higher currents and voltages. Bulkier than metallized versions. Summary of construction. Dielectric. Plastic film, polypropylene, polyester, etc. Electrodes. Metallized layer or metal foil. Winding. Layered or wound structure of film and electrodes. Encapsulation. Protective casing for environmental shielding. Terminals. Contact points for connection to circuits. This construction method allows for a reliable, efficient, and stable capacitor suitable for a wide range of applications, from signal processing to power electronics. How film capacitors work. Film capacitors function by storing electrical energy in an electric field that is created between two conducting surfaces, electrodes, separated by a dielectric, insulating material. In the case of film capacitors, the dielectric material is a thin plastic film. Here's a breakdown of how they work. 1. Charge storage. When a voltage is applied across the terminals of a film capacitor, the following occurs. Electrons accumulate on one electrode, creating a negative charge, while the opposite electrode becomes positively charged due to electron deficiency. These opposing charges generate an electric field between the two electrodes through the dielectric material, plastic film, storing electrostatic energy. 2. Capacitance. The ability of a capacitor to store electrical energy is determined by its capacitance, C, which depends on three factors. Surface area, A, of the electrodes. The larger the electrode's surface area, the more charge can be stored. Distance, d, between the electrodes. The closer the electrodes, the stronger the electric field and higher the capacitance. Dielectric constant, epsilon, of the plastic film. This is a property of the dielectric material that describes its ability to support the electric field. Equals epsilon. C equals epsilon. D. A. Epsilon, dielectric constant, different plastic films, e.g., polypropylene, polyester, have different dielectric constants, affecting the capacitor's capacitance. 3. Charging and discharging. Charging. When a voltage is applied, the film capacitor charges by accumulating electric charge on the electrodes. This energy is stored as an electrostatic field in the dielectric. Discharging. When the circuit demands power, the stored energy is released. The capacitor discharges as the electrons flow from the negatively charged electrode to the positively charged one through the external circuit. This process allows the capacitor to supply or absorb current as needed to maintain voltage stability in the circuit. 4. Role of dielectric, plastic film. The plastic film in film capacitors serves as an insulator that separates the two electrodes. It prevents the flow of electrical current directly between the electrodes, while allowing the electric field to exist between them. Energy storage. The dielectric is where the energy is stored in the form of an electric field. Dielectric breakdown. If the voltage exceeds the dielectric strength of the plastic film, the capacitor can fail, resulting in a short circuit or breakdown of the insulating layer. 5. Low loss and high stability. Low loss. Film capacitors are known for their low equivalent series resistance, ESR, and low dissipation factor, meaning very little energy is lost as heat. This makes them ideal for high-frequency and high-power applications. High stability. The plastic dielectric is stable over a wide temperature range, ensuring consistent performance even in harsh environments. 6. Self-healing mechanism in metalized film capacitors. In metalized film capacitors, a self-healing mechanism exists. When a high voltage creates a localized dielectric breakdown, the thin metal layer at the point of failure vaporizes, isolating the defect without affecting the rest of the capacitor. This self-healing property ensures continued operation and prolongs the lifespan of the capacitor. 7. Alternating current, AC, operation. Film capacitors are also used in AC circuits. In AC applications, the capacitor alternates between charging and discharging as the current switches directions. The ability of film capacitors to handle high-frequency switching without significant power loss makes them ideal for AC filtering and decoupling. Example, film capacitor in an AC motor circuit. In a motor-run capacitor, a film capacitor stores and discharges electrical energy to help maintain a stable voltage supply for the motor's windings. It smooths out any fluctuations in the power supply and improves the motor's torque and efficiency by providing a constant phase shift for the motor. Summary of how film capacitors work. Charge storage. Electric charge accumulates on the electrodes, generating an electric field across the dielectric, plastic film. Capacitance. The amount of stored energy depends on the surface area of the electrodes, the distance between them, and the dielectric constant of the film. Charging/discharging. Capacitors store energy when voltage is applied and release it when the circuit requires power. Dielectric function. The plastic film insulates the electrodes and stores the electric field. Self-healing. Metalized film capacitors can recover from small dielectric breakdowns by vaporizing the damaged part of the electrode. In essence, film capacitors store and release electrical energy efficiently, providing stability, filtering, and energy management in a wide range of electronic circuits. Applications of film capacitors. Film capacitors are widely used in a broad range of applications because of their high reliability, low loss factor, stability, and long service life. They are especially suited for applications that require high precision, high frequency, and high voltage. Here are the key applications where film capacitors are commonly used. 1. Power electronics. Film capacitors play a crucial role in power electronics, where they handle high voltage, current, and frequencies. Common uses include power supplies. Film capacitors are used in DC power supplies to filter and smooth out ripple voltages, providing clean DC output. DC-DC converters and inverters. Film capacitors are often used in voltage conversion circuits due to their ability to handle high switching frequencies. Power factor correction, PFC, in industrial power distribution systems. Film capacitors are employed to correct power factor, reducing energy losses and improving the efficiency of electrical equipment. 2. AC motors and motor-run capacitors. AC motor-run capacitors. Film capacitors are used in AC motors, particularly in single-phase induction motors, to provide continuous phase shift and improve torque efficiency. These capacitors help maintain a stable voltage supply to the motor windings. Starting and running applications. Film capacitors are used in both the starting and running phases of motors to increase efficiency and reduce energy consumption. 3. Signal processing and timing circuits. Film capacitors are highly valued in signal processing and timing circuits due to their precision, stability, and low distortion. Audio circuits. Film capacitors are widely used in high-end audio systems for coupling, filtering, and crossover networks because they have low signal distortion and excellent frequency response. Oscillators and filter circuits. In high-frequency circuits such as oscillators and filters, film capacitors provide stable capacitance and low signal loss, essential for maintaining signal integrity. Tuning circuits. In frequency-sensitive circuits, such as tuners and radio frequency, RF, circuits, film capacitors help in fine-tuning the resonance frequencies. 4. Automotive applications. Electric and hybrid vehicles. Film capacitors are used in automotive power systems to manage voltage, filter noise, and stabilize electrical systems in hybrid and electric vehicles, EVs. Power conversion and energy storage. Film capacitors help in converting and distributing power efficiently in the drivetrain and battery management systems. EMI suppression. In automotive systems, film capacitors are often used to filter out electromagnetic interference, EMI, and radio frequency interference, RFI, generated by onboard electronics. 5. Energy storage in renewable energy systems. Film capacitors are integral to the functioning of renewable energy systems. Wind and solar power. Inverters used in solar and wind energy systems use film capacitors to smooth and filter the electrical output, ensuring that the energy converted from DC to AC is stable and free of fluctuations. Energy storage systems. Film capacitors are used to store and manage the electrical energy generated from renewable sources, providing reliable energy storage and delivery. 6. EMI/RFI suppression. Electromagnetic interference, EMI, and radio frequency interference, RFI, can disrupt electronic systems, especially in sensitive equipment. Film capacitors are used in filters and suppression circuits to block unwanted high-frequency noise in power and signal lines. These capacitors are found in EMI filters, RFI suppression filters, and line filtering applications for electronic devices, home appliances, and industrial equipment. 7. Snubber circuits and power switching devices. Film capacitors are used in snubber circuits that protect power semiconductor devices like transistors, IGBTs, and thyristors from voltage spikes during switching. These snubber circuits are commonly found in power conversion systems, motor drives, and high-power inverters, helping to absorb and dissipate excess energy to prevent damage to the power components. 8. Lighting systems. In fluorescent and LED lighting systems, film capacitors are used for power factor correction, improving the efficiency of the power supplied to the lights. They also help in suppressing electrical noise and reducing flicker in lighting systems. 9. Medical electronics. Medical equipment such as imaging devices, diagnostic machines, and surgical tools rely on film capacitors for stable power supply and signal processing. The high precision, low noise, and reliability of film capacitors make them suitable for critical applications where performance and safety are paramount. 10. High frequency and radio frequency, RF, circuits. In radio frequency, RF, and microwave circuits, film capacitors are often used in filtering, tuning, and impedance matching applications due to their low dielectric loss and stable performance at high frequencies. RF transmitters, receivers, and communication systems benefit from the precision and reliability of film capacitors in maintaining signal clarity and strength. 11. X and Y capacitors for safety applications. X and Y capacitors are a specific category of film capacitors used in safety-critical applications, especially for EMI suppression and power lines. X capacitors are used between live conductors, line to line, to filter out high-frequency noise. Y capacitors are placed between live conductors and ground, line to earth, for safety purposes, preventing high voltage from leaking into the system. 12. Resonant circuits and inductive load compensation. Film capacitors are used in resonant circuits to tune circuits to specific frequencies, such as in inductive heating systems and wireless power transfer applications. In circuits dealing with inductive loads like transformers and motors, film capacitors provide compensation, improving overall system efficiency. Summary of applications: power electronics, power supplies, inverters, and converters. AC motors, motor run and start capacitors. Signal processing, audio circuits, oscillators, and timing circuits. Automotive, EVs, hybrid cars, and EMI suppression. Renewable energy, wind, solar power systems, and energy storage. EMI/RFI suppression, noise filtering in sensitive electronics. Snubber circuits, protection for power devices. Lighting systems, power factor correction. Medical electronics, stable power for critical devices. High-frequency circuits, RF circuits and communication systems. Safety applications, X and Y capacitors for EMI suppression. Resonant circuits, frequency tuning and inductive load compensation. Film capacitors' versatility and reliability make them essential components in a wide array of electrical and electronic systems. Advantages of film capacitors. Film capacitors offer a range of benefits that make them highly suitable for various electronic applications. Their advantages stem from their design, materials, and electrical properties, providing superior performance in comparison to other types of capacitors, such as electrolytic or ceramic capacitors. Here are the key advantages of film capacitors. 1. High stability. Temperature stability. Film capacitors exhibit excellent stability across a wide temperature range, maintaining consistent capacitance and performance even under temperature variations. Frequency stability. The capacitance of film capacitors remains stable at different frequencies, making them ideal for high-frequency applications like oscillators and RF circuits. 2. Low dielectric loss. Film capacitors have extremely low dielectric loss or dissipation factor, DF, which means very little energy is lost as heat during operation. This is particularly advantageous in high-frequency and high-power applications where energy efficiency is critical. 3. Long lifespan. Durability. Film capacitors have a long operational lifespan compared to other capacitor types, particularly electrolytic capacitors, which are prone to aging and wear over time. Self-healing properties. In metalized film capacitors, if a dielectric breakdown occurs due to high voltage, the capacitor can self-heal. The thin metal layer vaporizes around the fault, isolating the damaged area and restoring functionality without affecting the rest of the capacitor. This extends their lifespan and reliability. 4. High insulation resistance. Film capacitors have high insulation resistance, which reduces leakage current to a very low level. This is critical for applications that require efficient energy storage and low losses, such as timing circuits and energy storage systems. 5. Wide voltage range. Film capacitors can handle a wide range of voltages, from low voltages in signal processing circuits to high voltages in power systems, up to several thousand volts. This makes them suitable for a broad spectrum of applications, including AC motors, power factor correction, and high-voltage power supplies. 6. High ripple current capability. Film capacitors can withstand high ripple currents, the AC component superimposed on the DC and power supply circuits, making them ideal for use in power supplies, DC-DC converters, and inverters. 7. Low equivalent series resistance, ESR. Film capacitors have low ESR, meaning they can handle high-frequency signals and large current loads efficiently. This low resistance to AC currents reduces the amount of heat generated in the capacitor, enhancing performance in power electronics and high-frequency circuits. 8. High current carrying capability. Film capacitors can handle high current loads without significant temperature rise or degradation in performance. This characteristic makes them suitable for applications involving high peak currents, such as snubber circuits and power factor correction. 9. Non-polarized nature. Film capacitors are non-polarized, meaning they can be used in both AC and DC circuits without worrying about polarity. This simplifies circuit design and broadens the range of applications where they can be used. 10. Low humidity sensitivity. Film capacitors are relatively insensitive to moisture and humidity, making them reliable even in environments that may not be well controlled. This durability in harsh conditions is a significant advantage for outdoor or industrial applications. 11. No degradation over time, no drying out. Unlike electrolytic capacitors, which can dry out over time and lose capacitance, film capacitors maintain their performance characteristics throughout their lifetime, ensuring consistent and reliable operation for extended periods. 12. High dielectric strength. Film capacitors have a high dielectric strength, allowing them to handle higher voltages without breaking down. This makes them ideal for high-voltage applications, including power electronics, power factor correction, and motor run capacitors. 13. Low self-inductance. Film capacitors exhibit low self-inductance, making them suitable for high-frequency applications. This low inductance is beneficial in circuits like switch-mode power supplies, SMPS, and high-speed digital circuits, where fast switching and signal clarity are essential. 14. Environmentally friendly. Most film capacitors use non-toxic materials, and some types, like polypropylene film capacitors, are environmentally friendly because they do not contain hazardous substances like PCBs, polychlorinated biphenyls, which are found in some older capacitor designs. Summary of advantages. High stability in temperature and frequency. Low dielectric loss, ensuring efficiency in power applications. Long lifespan due to self-healing properties and durable materials. High insulation resistance, reducing leakage current. Wide voltage range for diverse applications. High ripple current handling for power supplies and converters. Low ESR and low inductance for high frequency and high current applications. Non-polarized, suitable for both AC and DC circuits. Moisture resistance, reliable in harsh environments. No drying out, unlike electrolytic capacitors, ensuring longevity. High dielectric strength, supporting high voltage applications. These advantages make film capacitors one of the most reliable and versatile components in electronics, offering long-term performance in applications ranging from consumer electronics to industrial power systems. Disadvantages of film capacitors. While film capacitors offer numerous advantages, they do have certain limitations that make them less suitable for specific applications. Here are some of the key disadvantages. 1. Larger physical size. Bulkiness. Film capacitors are typically larger than other types of capacitors, like ceramic or electrolytic capacitors, with the same capacitance value. This can be a limitation in applications where space is a concern, such as in compact electronic devices. The size tends to increase significantly as the required capacitance and voltage ratings go up, making them less suitable for high capacitance applications where space is limited. 2. Lower capacitance per volume. Low energy density. Film capacitors generally have a lower capacitance per unit volume compared to electrolytic capacitors. For high capacitance requirements, in the microfarad range or above, film capacitors need to be much larger than their electrolytic counterparts. This limits their use in applications where large capacitance is needed in a compact form factor, such as in power supply filtering or energy storage. 3. High cost. More expensive. Film capacitors are typically more expensive than electrolytic and ceramic capacitors, especially at higher voltage and capacitance ratings. The materials used, such as polypropylene or polyester, and the complex manufacturing processes contribute to their higher cost. In applications where cost is a key factor, film capacitors may not be the most economical choice. 4. Limited capacitance range. Lower capacitance. Film capacitors are not well suited for very high capacitance applications. While they can go up to a few microfarads, μF, they are not practical for applications requiring capacitances in the millifarad, mF, range or higher, where electrolytic capacitors are more appropriate. This limitation restricts their use in applications like large energy storage systems or bulk filtering. 5. Sensitivity to overvoltage. Dielectric breakdown. Although film capacitors have a high dielectric strength, they can still suffer from dielectric breakdown if subjected to voltages significantly higher than their rated capacity. Overvoltage can lead to internal damage, even in self-healing capacitors, and cause capacitor failure. Unlike electrolytic capacitors, which are more forgiving to momentary overvoltages, film capacitors can fail abruptly when subjected to excess voltage. 6. Limited to lower capacitance tolerances. Precision. Although film capacitors are stable, they often come with limited tolerance ranges, typically between plus or minus 5% and plus or minus 10%. If tighter tolerances are required, such as in precision timing circuits, other types of capacitors, like some ceramics or specially designed film types, might be preferred. 7. Temperature sensitivity in certain film types. While most film capacitors offer good temperature stability, some film types, like polyester or polystyrene, can be sensitive to temperature changes. Polyester capacitors exhibit higher temperature coefficients, meaning their capacitance can vary more with temperature. Polystyrene capacitors can melt or degrade at higher temperatures, limiting their use in high-temperature environments. For high-temperature applications, specialized film capacitors, like polypropylene, are required, but these tend to be more expensive and bulkier. 8. No polarization. While the non-polarized nature of film capacitors is an advantage in many applications, it can be a disadvantage in some situations. Electrolytic capacitors, for instance, are polarized and provide much higher capacitance for the same size when used in DC applications. In some cases, polarization is needed to handle specific DC signals, and the lack of polarity in film capacitors limits their use. 9. Poor performance at low temperatures. Some types of film capacitors, e.g., polyester, do not perform well in extremely low temperatures. The capacitance can shift and the dielectric material can become less effective, making them unsuitable for applications that need to operate reliably at very cold temperatures. 10. Not suitable for very high capacitance applications. While film capacitors excel in high-frequency and high-voltage applications, they are not suited for applications requiring very large capacitance, such as smoothing large ripple currents in power supplies or energy storage systems. In such cases, electrolytic capacitors are preferred due to their higher capacitance values in a smaller form factor. Summary of disadvantages. Larger size compared to other capacitor types for the same capacitance. Lower energy density, making them impractical for high capacitance applications. Higher cost, especially at higher voltage ratings. Limited capacitance range, unsuitable for very high capacitance applications. Sensitivity to overvoltage, leading to possible failure under excess voltage. Limited tolerance, less precise than other capacitor types in some cases. Temperature sensitivity in some film types, like polyester or polystyrene. Non-polarized design may not be ideal for certain DC applications. Poor performance at low temperatures for certain film materials. Not suitable for very high capacitance, where other capacitors, e.g., electrolytic, are preferred. Despite these disadvantages, film capacitors remain a popular choice for applications where high stability, low loss, and long service life are prioritized, particularly in power electronics, signal processing, and high-frequency circuits. In summary, film capacitors are crucial in many electronic circuits for their reliability, stability, and performance, particularly in power and signal processing applications.